Yeah, okay. Thanks everyone for coming. This is, yes, my PhD defense. And I'm going to talk to you about some of the work I've been doing over the last few years. I've been focusing on making improved predictions of waves along our coastlines using buoy observations as well as predictions from global wave models. So we'll be looking at Southern California, which a lot of you are familiar with. So with that, let's get started. So first, we should just acknowledge that wind drives waves. The greater the wind, or the faster the speed of the wind, the longer it blows for, and the greater distances that it blows over, which we often call fetch, the bigger the waves you're going to find. Wave predictions has a long history. If we go back to 1944, Walter Munk and Sverdrup with some empirical relations, made predictions of what the landing conditions would be at Normandy on D-Day. And this was particularly important because waves, I think over 6 feet or so, Walter said, would have sunk the landing craft. So this was an important time in our history where we needed to know what the waves were near shore. If we go a little bit further into the future, the National Weather Service started making computer-aided wave forecasts back in 1956. However, these initially only considered local winds. So whatever the winds you saw, say outside on the waves today, those would be the winds you'd assume generating the waves you saw. However, as our understanding grew, we began to realize that waves could travel vast distances. And in 1963, a very ambitious experiment, but a very cool one, driven by Walter Munk and others, called Waves Across the Pacific, measured waves originating off Antarctica in the southern hemisphere during a particularly violent southern summertime storm. They measured these waves traveling all the way across the Pacific at these various stations you see there on the map. And so they watched this wave energy travel all the way to Alaska. And they found that it dissipated relatively little, or a lot less than they thought. So waves arriving in our beaches today can come from all the way from Antarctica, as well as from the North Pacific, like off the Aleutian Islands. These waves that we think of that travel from great distances are often called swell. They are called swell when they outrun the winds that generated them. As history progressed, we started to get a better understanding of how waves grow. Swab, where they looked at waves in the North Sea, gave us better empirical understanding of the relationships between wind speeds, time, and the detailed spectral shape, so that energy in the waves is a function of frequency. In 1985, third-generation wave models were developed, and these were important because these modeled wave spectra in a complete frequency directional sense, and we'll talk more about this soon. But with this, they were able to model detailed growth, decay, and nonlinear interactions. And since '85, since we started using these third-generation wave models, they've only improved. And this has been due to improving coverage of global wind stress by global satellites. So satellites fly over using scatterometers, measuring the roughness of the ocean's surface, and they can translate this into the stress that the wind is pushing on the surface and estimate wind speeds. This information goes directly into global models, estimating the wave conditions and wave propagations. So in addition to improving the parameterizations, better physical understandings of some of these wave processes, we've also had much faster computers, allowing us to improve our numerics and our resolutions. So wave prediction has come a long way in the last, I think that's almost 80 years. And why do we even care about it? Let's get back to that. Well, we cared about it on D-Day, but in general, a lot of the energy a lot of the energy that goes into waves in the ocean ultimately arrives at our coastline and dissipates in the form of breakers. And this drives a lot of nearshore processes. So whether you're on a low sloping beach like here at Scripps, having the breakers roll in nice and slow, or a cliffside where the waves smash right into it, you'll have a few different processes at work. One of them, transport. This can happen in the cross shore, but also in the alongshore. When waves come in at an oblique angle to the shoreline, they set up, they generally drive an alongshore transport. So you can see these waves here arriving at the shore at an angle, and they're going to push water, as well as sediment, biota, pollutants, or anything else in that water, and it's going to drive it in the direction that the waves are obliquely incident. In addition to transport, waves incident on the coast can cause erosion of cliff sides and beaches, and this is particularly important where we have infrastructure and homes. And lastly, in lower lying regions, and notably getting worse with sea level rise, we have, or during large wave events, the water surface is elevated, and this can cause flooding in regions like this. So ultimately, for both regional communities as well as coastal research, we want accurate coastal wave predictions all along our shores. So how do we do this in our modern day era? Well, we're sort of two independent ways that this kind of happens right now, and we'll talk a lot about how they differ and how I'm working to put them together. But on the left, what you see are predictions from NOAA's global wave model called WaveWatch 3. I'll be referencing this a lot as I go. And in color, what you see is wave heights predicted in the Pacific Ocean, and you can see it covers all of the Pacific. These are driven by those satellite observations and those global wave model numerics that we talked about earlier. So this is one way you can make predictions of waves. Now on the other side, before these global models got so good, if you wanted to know your regional waves offshore, you had to put some kind of instrument offshore. And oftentimes this was a floating buoy. And so all those black dots you see, those are all along the California coastline. These are run by the Coastal Data Information Program, CDIP. And these buoy observations of waves can be used independently to drive sort of their own smaller regional wave models. So now some questions start to arise as, well, now that global model skill is so good, how does it compare to our regional buoy-driven models? And how do we start to combine these two approaches? And what does this mean for buoy observations going forward? So with that introduction, this is the outline of the talk. First, I'm going to go over some background, talk a bit about wave spectra, some details, and what buoys observe in relation to that wave spectra. Then I'll show you some brief comparisons between buoy-driven and global wave model-driven predictions in the near shore. Which ones do better? Which ones do better? Okay. And then I'll get into a general method that I've developed to combine these nearshore buoy observations with global model predictions. And lastly, I'll show you what kind of implications this has for buoy array design. These last three sections come from two papers, one published last year and the other currently in review. So, wave spectra. So oftentimes as surfers or beachgoers, when we think about waves, we think about just a couple numbers, like significant wave height, or maybe peak period, or maybe the direction. But when you look out at the waves, and sometimes more of a chaotic sea like this, you see lots of different wave crests at lots of different heights with different wavelengths, and coming in at different directions. And so really these sort of bulk parameters, we can call them, don't sufficiently describe the wave field, especially when you're concerned with modeling the waves' propagation to near shore. So in models, we consider what we call the frequency directional wave spectrum, the wave spectrum for short. And this plot here is a wave rose, often called a wave rose. And what you see in color is the energy in the wave field. This is a statistical description of the wave field, and it tells you how much energy is in each frequency and direction. So in the radial is the frequency, and in the azimuth is the direction. And so this is sort of typical conditions for Southern California, where we have some moderate frequency wave energy coming from the northwest, and a little bit of wave energy coming from the south, at a bit lower frequency, this longer period stuff that comes from farther away. So how does this look? If you looked out at the ocean, what might these wave conditions translate into your actual site? Or if you look at a plan view, like a top-down view of the ocean surface, here's one random realization of what those crests might look like. And just to give us a sense for how these directions, or how the spectrum translates into actual waves in the field, we started with some southwest energy from very long period waves. You saw those organized crests. And now we'll interject some northwest energy and some higher frequency. You can see much shorter wave crests inside a slightly more chaotic wave field. So we'll be focusing now on this wave spectrum in frequency and direction space. But when you're thinking about the actual waves, it might look something like that. So now I'm going to tell you why we care so much about getting the details of this right, especially in sheltered regions like Southern California. So here's Southern California. At the top, you see it extends from Santa Barbara down to San Diego, where we are right now. And offshore, we have the Channel Islands. And so what I'm showing you in this animation is wave heights in the region for varying offshore directions. So this is very narrow incident swell. And what I'm showing you is, well, what it's supposed to illustrate is that with very small shifts in direction offshore, we get very large differences in the wave height along the coast. And so if you just pick a point as the direction changes along the coast, you see that quite rapidly the region is either sheltered or focused. And actually, sorry, I forgot to explain the colors. So the white is just 1 meter wave heights offshore, and then blue is lower wave heights, indicating the sheltering in the region, and red is focused wave heights or larger wave heights. So anywhere you're kind of blue means your wave heights are really low, but then it gets white all of a sudden, it might get red as these wave directions shift. So you can imagine if you're trying to make good wave predictions in this region, you need to know the distribution of waves in the offshore, what directions they're coming from, and you need to know this quite accurately, or you're going to make some rather severe errors in the near shore. So that brings us to directional wave buoys. So these are very common wave observing instruments, and they are designed to float and follow the wave crests, generally in this circular motion, as they bob around. And by measuring the vertical and horizontal displacements, we can get some estimates of that wave spectrum, but we don't get a complete picture, and this is important for us going forward. So this wave buoy gives us some idea at each frequency of the energy in that frequency, the mean direction, and some higher order directional moments. But it doesn't tell us everything about direction. And to give us an analogy, this is something that my advisor Bob Guzet often says to me, is looking at the waves through a buoy's lens is like looking through a Coke bottle. It's all blurry and distorted, and maybe that Coke bottle is shaking. So you might have some idea where the waves are coming from, but you certainly couldn't tell us the detailed directional spectrum. I'll give you an alternate analogy that I like just a little bit more, where looking through a buoy's lens is like removing most of the rods and cones in your eye, and you're only getting a few pixels and only a little bit of information about what's going on. So with these analogies, let's see how this plays out when you try to estimate the directional details using this wave buoy information. Like I said, these low order pieces of information, the mean direction and some higher order moments. So if you're going to draw a directional spectrum, and that's what this plot, this blank plot here, is going to show you. The x-axis is the direction, and the y-axis is the amount of energy coming from that direction. So it's a distribution of the energy at varying directions. If you need to make an estimate of this from this limited information, you need to impose some additional constraint. A commonly used constraint is called maximum entropy, where this spectrum maximizes entropy, but fits the information the buoy measured exactly. However, there are lots of other subjective priority constraints that you can impose, including exponential roughness, often called the Bayesian direct method, or just roughness in a second derivative sense. And so you can see that these different directional distributions of energy, they all fit the buoy data exactly. And the point I'm trying to get across here is that the directional spectrum, as measured from a buoy, is non-unique. It could be any of these three curves or any another, like infinite many different curves using different subjective constraints. And just to make that problem a little bit harder, buoy observations, these directional moments we measured, have some statistical uncertainty associated with them because the buoy only measures for a finite period of time. And so these limited degrees of freedom actually give us, or provide, well, there's uncertainty in these low order moments. And if you propagate that through some of these various methods to generate a complete directional spectrum, you get a very blurry picture indeed. So the takeaway message here, the takeaway message here for buoys is that they're both non-unique in their measurements and blurry due to statistical uncertainty. So how does this compare to our global wave model predictions? Because they have different advantages and disadvantages. So this red line I've thrown up here in the plot shows you an example of what global model predictions might look like. As I mentioned before, these third-generation global models, they make predictions in complete frequency directional spectral space. So you get in this discrete estimate of what this direction distribution might look like, and it could look like something like there in red, where there's a certain resolution. Right now it's 10 degrees. And while this looks good, we don't know how correct it is. There are biases and uncertainties in global model predictions. If they were perfect, we wouldn't be here right now. So on one hand, we have blurry buoys, and on the other hand, we have some wave watch 3 predictions that are uncertain. So now the first question is, well, how well does each one do? So this is section 2. So let's just take a quick review of the pros and cons associated with each technique. So on the left, we can use global model predictions. We'll be using NOAA's Wave Watch 3. These look something like this for the region. They're a little bit coarse, but we can use their coarse observations offshore and run them through our regional model. The pros are that they're freely available, and they do also make forecasts. The cons are they can contain some uncertainty and bias, and we don't know exactly what those areas are. On the other hand, we have regional models like CDIPS, where they use the buoy observations. We know the uncertainty in buoy observations, however, they contain directional ambiguity. And additionally, buoys are costly and they don't make forecasts. So how well do we do in terms of wave height predictions in the region? Well, here's a quick and dirty look. In purple are prediction errors. So this is the average error you might expect in wave height predictions for the area in purple. And you see that ranges from about 25 to 35% in the region. And the buoy-driven equivalent ranges from about 15 to 30. So you're definitely buying something by having the buoy offshore and running predictions in this way that CDIP does. So buoys give us something. Now, these are significant wave height predictions, but I also mentioned that waves drive processes like transport. While those predictions don't look super huge, we can take a look at transport where things get a little worse. So to look at transport, we're not going to actually estimate a whole bunch of complex processes, but we're going to just stick to this first order estimate that we can, first order property really of wave energy incident along the near shore. So the alongshore radiation stress driven by obliquely incident waves, commonly referred to as X subscript XY, can be used as a proxy for transport. To first order, it's nearly proportional. So this plot here shows you this alongshore radiation stress on the y-axis, and on the x-axis you see various buoy sites where we've used the buoy observations to measure this. So these are observations of this alongshore radiation stress for which we'll just use as a proxy for transport right now. And now the question is, how well do we predict this? First with our global model. And so right now, I'm showing you in blue predictions of this transport proxy from Wave Watch 3. And you can see that at some regions it does well, but at other regions we have pretty significant errors on the order of about 2x. So this is the ocean side. And then additionally down here in the Santa Barbara Channel. I should say that positive values are northward transports and negative values are southward transports. Now if we use buoy-driven system, using those buoy observations offshore, we see a bit better skill in our estimates of transport in the near shore. And you can see here that we've more or less corrected errors at oceanside. However, biases still remain in the Santa Barbara Channel. Now, I forgot to mention, but these transports are your yearly average transport. So if you're thinking about long time scales, where are things approximately going to go? Now, I did mention that buoys have this ambiguity. So I've thrown up an alternative buoy-driven system. Like we could have picked maximum entropy, we could have picked roughness. So here, just to show you how much that influences this problem, you can see that this green dot is a different buoy method. And what you see is that at some regions, at some regions like Oceanside, it biases and actually is quite wrong. However, in other regions like the Santa Barbara Channel, it seems to get it right. So there's really no golden ticket with buoy estimators and what constraint you pick. You just get different answers. So to summarize section 2 briefly, we see that using buoys, despite their directional ambiguity, does give us better prediction in the near shore. However, alongshore transport errors can be comparatively large. All right, so now into section 3. This is the most interesting one, I promise. So I'm going to show you a general method developed to combine these near-shore buoy observations and offshore buoy observations with global model predictions. But first, I'm going to use something tangible to give us an idea about where we're going and how it might work. So we're taking the most common image found on the internet, and suppose this is observed by a few different individuals. However, each of them has really horrible eyesight. But the advantage is, but the unique thing is that they saw this cat from a different point of view. So maybe this one saw it from here, and he had this horrible buoy vision. And then this guy saw it from here, and then she saw it from here, and anyways, so on. So we had a lot of different individuals, and they all saw this cat sort of from a different angle, so maybe some got a better view of the tail, some got a better view of the head, but they really had this horrible pixelated vision. Could we not take all of this information, put it together to create a more high-resolution picture of the cat? So combine all the blurry information to make something more clear. Well, that's the idea. Oh yeah, that's what I basically was going to say. So we're going to use a low-resolution cat because the computer can only process so much. But let's take the first person and we say, hey, you need to reconstruct this image you saw. We're not telling you it's a cat, but we are going to tell you it should be somewhat smooth. And so maybe they drew something like this on the right, where really you're not sure what that is, but it did get the dark spots where they should be dark. Now we add a second person to the mix. They get to chat, and they draw their smooth picture of the image. A third person, and then a fourth, and fifth, and we keep adding more information, and you can see that we're starting to get a bit more idea of what's going on in this image. It almost looks cat-like. And there, it's cat, but it's a bit blurry. It's like a blurry cat. Okay, so this is the idea, is we're going to take a bunch of people with really blurry eyes, and we're going to ask them to reconstruct this given their unique information. And that's what's going to be happening with the buoys and this offshore spectrum, this offshore wave spectrum that we want to get quite accurately. So here we are again in the Southern California bight, and each one of those dots are buoys. And you can see sort of illustrated with these red open windows that each of these buoys is sheltered in a unique way. And so it's seeing a unique part of the offshore spectrum. And so even though each one of their pictures is blurry on its own, given these different look angles, we're going to try to create a higher resolution, more accurate picture of those offshore wave conditions. And the thing we're going to add to this that we didn't have with CAT was that we've got this global wave model offshore, and it's got valuable information because we know it makes good predictions, but we know there's some things wrong with it. So we're going to start with this global model prediction offshore and sort of adjust it with the buoy information in the near shore. So this is like saying, here's a rough outline of the cat, work with that. So to do this, we're going to need to be able to model waves efficiently and easily into the near shore. And so we've used a simplified forward model considering just the linear propagation physics for waves. And you'll see why this makes the problem easier in a second. But we're only going to be considering shoaling and diffraction and sort of throwing out those higher order wave terms there in the red X's. So we've tested these assumptions in the region and to see which frequency bands they work for. And so here what you see are some buoy locations off of Southern California and the Southern California bight. And what I've done is taken predictions from the global wave model at these sites. So it's sort of an internal test of if the global wave model contains all these additional physics, if we make some linear assumptions like for what frequencies, for what distances, do these hold? So taking the predictions at the black site, we can use those in our linear framework and make predictions at those colored sites further south. So how well do those predictions hold up to the actual model with all the real physics? So that's what I'll show you here on the right. R-squared is a metric of skill. That's on the y-axis. On the x-axis is frequency. And what you see for the blue one is you get pretty high skill for most frequencies, but as you get further away from your initial prediction site, you see the skill starts to fall off, and it falls off quite fast. I know that's a little blurry, but that's 0.09 hertz, so I've drawn that dashed line and sort of used that as our cutoff. So we're only going to consider wave energy in this realm in which we consider that the linear assumptions of wave propagation are good enough to model the actual wave propagation. So this range, this frequency range between 0.04 and 0.09 is often sort of thought as the swell band. This is the wave energy that surface like the most. And for the region, it covers about 60% of the energy flux coming in. So there's a total different, harder problem on the right side of this frequency spectrum that we're not considering here. Maybe that's for someone else's PhD. So how do we measure, or how do we model these linear wave processes, this refraction and Schollen? Well, we've used backwards ray tracing techniques to relate the nearshore sites to the offshore directions. And using ray tracing is advantageous because we can do it at a very high resolution. And tracing these rays gives us this relation that allows us to develop a transfer function between offshore energy and nearshore energy. And so this plot right here on the y-axis shows you the ratio of the nearshore energy to the offshore energy. So where this is 1, this site is unsheltered to those directions. On the y-axis are the offshore directions. So this is Torrey Pines buoy site, and what you see is this is approximately 1 between about 180 and 260 degrees or so. And so under these directions, Torrey Pines is unsheltered, and wave energy that's offshore comes right in. Where this is greater than 1, there's some focusing happening. Where it's less than 1, there's some islands in the way, or some bathymetry features that directs energy away from the region. So these are our transfer functions, and because ray tracing isn't used that often in the literature, I've compared this to transfer functions derived from a more commonly used wave model, SWAN. And so what you see here in comparison is that they're actually really quite similar. This modern frequently used wave model seems to produce very similar transfer functions for this region. However, you see it's a little bit smoother, but that is expected given that these kind of numerical models tend to smooth stuff out. Now we've got our transfer functions. We're able to write our wave model in this really simple linear equation, H, which is our transforms, and X, our offshore wave spectra. We can do this on a frequency by frequency basis, so we're just going to pick one frequency for now. It's a function of direction, and that's going to give us our predictions at our nearshore sites. So our wave model is this nice linear equation. So if you forgot the question, we are trying to find an offshore wave spectrum that is consistent with our data in the nearshore, as well as consistent with the wave watch 2 predictions offshore. We're going to find this by minimizing this cost function. We minimize, in the red, the misfit to observations, weighted by their uncertainty, which is something we know, plus the misfit to the wave watch 3 predictions offshore, weighted by an uncertainty that we have to specify. And then lastly, we're going to minimize roughness of the spectrum. We believe that in some sense, the wave energy in frequency and directional space is smooth, so we're going to impose this roughness penalty. And lastly, this spectrum is energy, and negative energy is non-physical, so we have to enforce this positive constraint. For the linear algebra folks out there, this is how it looks like in its beautiful matrix form. You can see the misfit to observations weighted by their covariance matrix, and the misfit to the model prior, or the wave watch 2 predictions, weighted by their covariance matrix. So how does this work out? Let's take a look at a case study. It's just one event. So what I'm showing you here in color is wave energy predicted from the global wave model. And on the x-axis is time, on the y-axis is direction. You can see that this is a short event lasting just about a day and coming in from about 280 degrees. So this is at the peak frequency of the event. We're just doing one frequency at a time. Now we also have these observations out of buoy sites, and they observed energy and some of the directional information. Here are their energy observations. Again, the x-axis is time and the y-axis is energy, and we're looking at one offshore buoy site and 3 nearshore buoy sites. So this is just a subset of the observations available. If we take the WaveWatch 3 predictions offshore, run them through our forward model, we see there in the dashed blue those predictions, just given the WaveWatch 3, no alterations. We see some misfits at the observation sites. Now if we go ahead, take our WaveWatch 3 information, take our buoy information, put it in our cost function, we can find a spectrum offshore that's consistent with all of our specifications. And that looks like this. We'll call it our inverse spectrum. And what you see is that it is smooth as we made it. It is similar to WaveWatch 3 as we enforced it. And if we run this back again through our forward wave model, we see that it has good agreement with the data as we expected. Now what about the other buoys in the region? Do we, using this spectra that we inverted for, do we find better agreement at independent validation sites? So we'll take a look at a few of those. In this case, we see that we do, on average, get some better agreement at those other buoy sites. And on average, looking at a few different case studies that we used, we saw that we get a reduction in wave height errors of about 30% and mean direction errors of about 5 degrees. So overall, we think we're getting closer to what the true spectrum is offshore, which is ultimately providing us more accurate predictions in the near shore. So there are some regions where, I'm going to blow this one up, where we're still pretty far away from the observations. Now, even if we take this buoy site and throw it into our assimilation procedure, our inverse procedure, trying to get the model to fit it, we only find that the fit increases mildly. And so this large misfit here between the observations and the sort of this inverse spectra predictions indicates what we think is forward model error. I think in concept the idea is we're trying to find some offshore spectra that's consistent with all our data and our assumptions. And what we find is that it's consistent with most of our data except for maybe a certain buoy site like this one located here in the Santa Barbara Channel. And so what's likely happening here is that there's some error in the forward model that's just not allowing us to get enough energy in. And so we'll talk a little bit more about this region, the Santa Barbara Channel. It is notorious for making difficult predictions, or it's notorious for making predictions. It's difficult. So in a more comprehensive view, we can look at these biases that we saw when we tried to fit the data and look at them over all the case studies we looked at in all the buoy locations. So what I'm showing you in this plot here is observed energy on the x-axis and predicted energy on the y-axis. And so where these dots fall off this line, there is a large residual or a large bias. And just to premise, all of these observations were included in the assimilation procedure in this inverse. So they should all fit if the forward model was perfect and our data was perfect. However, what you see is that in general, they have a bit of a low bias. And these ones highlighted in red are all in the Santa Barbara Channel. And you can see they seem to dominate sort of the largest biases we observed. So something's happening there, whether it's some significant reflection off the Channel Islands, or maybe diffracted energy. That's not something we modeled in our linear sense. Coming around point conception is possible. Also, you'll notice that overall there's an underprediction, which is a little surprising given that there's no dissipation in the forward model. And if anything, dissipation would have given us a positive bias. However, it's possible that maybe there's some reflection bouncing around in the region. Low-level reflection does tend to come off beaches around 10%. So this could be attributing to our negative bias in this forward model. So in summary to this section, we saw that we were able to develop an assimilation technique that does improve regional skill, so it improves skill at validation sites. And this was done by reducing the uncertainty in the offshore boundary condition, sort of getting that offshore spectrum better resolved with a number of blurry pictures. And then second, we are also able to identify regions of forward error, regions where we could not fit the data. Previously, we weren't sure if there were errors in the offshore boundary condition that were causing these errors in the nearshore, or if it was the forward model itself. And so now it looks like it's likely the forward model itself. So lastly, the last section is sort of what kind of implications this work has for array design. Where do we put our buoys? How many buoys do we need? So we can play some games using varying sets of buoys in our assimilation and examining skill at validation sites in the region. And what you see overall in this figure here is that adding additional buoy sites tends to lower errors. So on the y-axis, we have root mean squared errors for significant wave height and mean direction. And on the x-axis, we have the buoys used in this inversion, in this assimilation. And we start on the left with no buoys, and that's called wave watch 3 only. So if we just had global models, we'd have higher errors. And as we add buoys into this process, as we add more information, we seem to decrease errors at validation sites, indicating overall regional skill improvement. Now, we can sort of start to play games with, okay, well now you can quantify the skill added per buoy. So if we just had one buoy, and it was an offshore buoy, and we wanted to add one more buoy, we might pick this buoy here. So in that 2 buoy sort of set of combinations, I've looked at adding different second buoys. And it looks like if you add buoy D8, you kind of get the best overall bump in skill. This is Torrey Pines buoy located just offshore here. Let's go back real quick. Okay, so that's kind of a fun thing to do. That can help aid in array design. Now, we can also think about directional buoys, knowing that they're pretty expensive. And part of that's getting some of the directional parameters really accurately with quality accelerometers and GPS. However, we could consider using just energy-only, cheaper floating devices or pressure sensors or some alternative wave observing thing. Something that maybe forgets about the directional information but tries to just get the energy at each frequency. And so by throwing away all the directional information in the nearshore, we can do the same procedure and see how much difference that information makes. And so what you see here in the dashed line is just that. All the directional information has been disregarded in the inversion. And we see that you only get modest gains by including that directional information in this approach. So maybe that directional information in the nearshore is less valuable than it is in the offshore, or just less valuable overall. And so maybe going forward, we have more inexpensive observations in the nearshore. Oh, there, that's the point. Okay, and then lastly, this sort of technique to assess sort of the optimal array design really only considers existing sites because you need the buoy data to put into this method. However, you can consider the open windows that each buoy has collectively and think about, okay, well this is my array, my buoy array, and it has a theoretical resolution associated with all the different angles we can see. I won't get into the details of how you can estimate that, but it's quite simple. And you get this, you can get a mean sort of average resolution, like how good theoretically is this existing buoy array or this theoretical array going to be. And so I've estimated that for these various buoy combinations. And what you see is as you add more buoys, the array resolution increases. But interestingly, as you add buoy D8, that best second buoy I said before, it also seems to give the highest theoretical resolution to the array as opposed to those other 2 options for adding a second buoy. So this is a little bit of a dangerous thing to start doing if you're unsure whether your forward model works or if you're if you're unsure whether your forward model works because you're not really considering whether it works or the uncertainties really inherent in your observations. However, this does seem to link up somewhat with the actual evidence given the observation. So might be another approach to figure out what sort of the best buoy sites to have on and what might add the most regional skill. So with that, I'll summarize all the chapters. In section 2, we saw that buoys are valuable. They improve skill in the near shore. They are currently better than the global model predictions. However, global model predictions will continue to improve. In the section 3, we saw that a computationally rapid assimilation method seems to work. It works for swell. This is that lower frequency wave energy, and it can help us identify regions with model error. And lastly, these kind of methods can aid in buoy array design. The initial results suggest, as you saw in that previous figure, that maybe after 1 or 2 or 3 buoys, you're not really buying a lot more information. And at least for swell, that might be sufficient for the model. So with that, I just wanted to end on some statistics. It's currently day 2037 of my detainment, and there have been about 4,100 MATLAB scripts written or copied, about 1,500 emails from my advisor, which I all appreciate very much, and I incorporated some of them into this word. I forget what you call it. Apparently model is very important, so is buoy, which is good. And there have been a lot more emails from the SIL listserv, and only 2 surfboard snapped, which I think is pretty average, really. Okay, so before I get to questions, I just want to acknowledge everyone that's helped me get here. I wouldn't be here without all of you. This includes my mentors, my committee, the lab, the grad department, my family, of course, my partner Aaron, my cellmate Julia, all the other basement dwellers, and the many friends I've made here. And yeah, so anyways, thank you all very much. I'll take any questions.